Hey everyone, Brian Beeler and Kevin O'Brien coming to you from the Storage View Lab. And today we're taking a look at something a little bit different, something in the cloud. So it's not sitting here in front of us, but we've spent some time on Oracle Cloud before. It's been a little bit, but I know you ran through the bare metal instances a while back.
It was fantastic. You looked at a lot of the other hosted solutions, and some were either limited by networking interconnect speed for additional block storage, other things. And Oracle came in with fantastic local performance, fantastic shared storage performance.
Right.
That really just blew away everything else.
Well, back when we were looking at that, it was the fact that they were enabling NVMe storage, which was one that most other clouds weren't doing. But the second thing is that the networking backbone was much more advanced for the interconnects between nodes, and that's something else that a lot of cloud providers weren't really working on.
Yeah, they were on 25 gig Ethernet, where everyone else is standardized around 10 gig, which gave them a huge benefit. So if you were expecting 1 gigabyte a second peak speeds on another provider, you'd be able to get 2.5 gigabytes a second for your attached block storage from them.
And so it's one thing to have a bunch of different instances and go after bulk workloads in the cloud, but some workloads really can benefit from a more robust infrastructure, to Kevin's point. And Oracle's been expanding on what they're doing in the cloud. They now have support for, at the end of April, for Intel Ice Lake CPUs. They've bumped up the networking. And we're going to talk a lot about that today with Kevin Jorson, who we'll bring in from Oracle Cloud. Now, Kevin, we're talking today specifically about HPC instances in Oracle Cloud, and you're going to demo that and walk us through all of those capabilities. At just a high level, tell us what you're doing over there and why Oracle's made such a commitment to this particular part of the cloud.
Hi, yeah, thank you very much for the introduction. So my name is Kevin. I'm a distinguished HPC architect here with Oracle Cloud. I first got interested in the cloud back when I was working in science and just couldn't fit the molecules I needed to study in the departmental cluster that we had available. And so the cloud was a place to go and get extra capacity and a place where you could solve bigger questions that didn't fit in what we had available on premises. So today I work with all of the HPC customers that Oracle Cloud has. And what I like about Oracle Cloud's approach is that we decided to go solve the hard problem first. We decided to build HPC capabilities that have enterprise-grade performance, security, and so on. So to basically give you the same performance that you are used to seeing on premises. And the reason that we started talking today was the launch of the new Intel Ice Lake HPC servers on Oracle. They came out about a month ago at the beginning of May. And lots of our users, of course, are now keen on giving those a try, seeing how much more performance they can squeeze out of those compared to the previous generation that we offered, which were Skylake servers. And that's another reason that some people like being in the cloud. Sometimes it's just about more capacity. At other times, it's about access to the right kind of capacity. So currently, if you come to Oracle, you can log into an account and you'll have access to a modern AMD processor, a modern Intel processor, a modern ARM processor, GPUs and whatnot. So you have some of everything, and you can always pick the right tool for the job.
Well, let's just jump into it, because I think that's what we want to see is some of these things that you're talking about and show us how they work and what the options are. So let's take a look at what we've got going on.
Sure, yeah. So what you're looking at now is my Oracle Cloud account. Yours will look just the same. And within your Oracle Cloud account, you can access a whole range of services. The one that you might think of first, perhaps, is just compute instances running servers in the cloud. Like any cloud, we have regions all over the world. Here we are now in the US East region, and we can say, I need a server. For example, I need an AMD server today, or let's wait a second for this to load, or I want an Intel server, I want an Ampere server, or something else. The selection box up here also lets us choose bare metal machines. If you're doing high performance computing, you're often going to want a bare metal machine because it means that you're not using the cloud provider's hypervisor And so that's one less barrier that stands between you and getting the absolute best performance out of the server that you choose. Let's see, let's go select the bare metal here again.
So when you're looking at the instance types, where are the more focused for HPC offerings, or would you consider most of the bare metal acceptable for that kind of workload?
Well, so most of the ones in the bare metal category would be reasonably acceptable for high performance computing work. But we are going to be particularly interested in the ones that have the low latency network support. So that's the 1.6 microsecond RDMA network. And what that's going to do is allow multiple HPC servers to communicate with each other at the very low latencies and the high bandwidths that are required to make one big HPC model run efficiently across a range of HPC servers. The one I selected now is the new Ice Lake instance type. This is what it would be called in your cloud account. Further down the list here also is the previous generation. This would be the Skylake server. These are two very typical choices to make for our HPC customers.
So you'll continue to keep those older instances around for some period of time?
Yeah, for sure. We are very mindful that we do not want to force our customers to make any changes to their infrastructure that they might not be ready for. HPC architectures can sometimes be quite sensitive to details. And so we generally continue to support older instance types for many years before finally deprecating them. That said, we are offering the new Ice Lake server at the same cost per core hour as the older Skylake. In other words, you're getting the performance improvements of a newer generation without a change in price. And so for our customers who do have flexibility, it will be kind of a no-brainer in sense of upgrading to the newer server type. But yes, we keep the older generations around for quite a while because there's always going to be customers who prefer not to change immediately. Well, so with that selected, you could go ahead and create a server, and then afterwards you could log in, you could install software on it, or you could treat it like any other server. There's lots of other services available as well. There are, of course, databases. There is storage, for example. Here is my object storage. Again, you're just looking at my account here. I want to apologize for it's the warmest day of the year here in Seattle. We're on our way to 110 degrees, and so if you can see me warming up a little bit, please bear with me. It's just in the once in a century heat wave. So my house, unfortunately, is not air conditioned. But here, for example, we see a bucket where I have a whole bunch of HPC-related files waiting to be used. In this case, you see a lot of files named WRF something, which is a type of weather forecast that I specialize in. However, even though we've now seen some of the mainstays of cloud, like servers, objects, and whatnot, when you want to do HPC, you typically are looking for, let's go look for an architecture diagram, for something more like this, for a cluster. In this case, what you see here is a group of instances. We call that the instance pool. All of these would be bare metal HPC servers. They would all be connected over a low latency network. They might have high performance storage attached to it as well. They can talk to a little bastion host here, which is little more than an access point. So the cluster itself sits safely in a subnet that's not accessible from the internet. But then here we have a bastion, an access point that is in a public subnet that can be accessed. And then you sitting here, or it says customer data center, or it could be your house or your office building, of course, can connect into the bastion and submit your jobs that will execute on a cluster. That's typically what you're going to be doing as an HPC user. And so, in order to do that, you're not going to go here and launch instances one by one, because that would not be a very good way of setting it up. So what you might do instead is you could come to the Oracle marketplace, where there's all sorts of software solutions that you can find here. And there is one called the HPC cluster. It's provided by Oracle. We update this as needed. And what this is going to do is basically it's going to set up this whole thing in one step, just to make it quick and easy for you. And
so do you just specify the amount of compute or nodes you want? What are the variables or levers here?
Well, let's click on Launch Stack and find out. So when I say launch me this cluster stack, I'm going to walk through a screen or two where I have an option to put in some various parameters. For example, we could give this cluster the name demo HPC or something like that. And then in the next screen, I will have an opportunity to do things like, say, where is it? For all my compute nodes, I want them to be of the HPC server type, which we saw earlier. And I want to have 10 servers, for example. That can change later. Once you set up the cluster, you can allow the cluster to change in size and, for example, attract additional nodes if you want to put a very big job in your scheduler. But we could start with 10, for example. Let's see, what else are we going to do here? Let me just choose where in my account I'm going to run this. Here I'm choosing just a data center, and then I'm going to copy in a public key that I will use later to SSH into the Bastion hosts. And I think those are the only settings that I absolutely have to touch.
Speaking of the data center, where do you have these HPC instances?
They are available in about half of our data centers, and so we have some HPC regions, as we call them, on every continent. See the,
okay.
I think I forgot to select one. There we go. So right now, for example, I am in Virginia, in Ashburn, but we also have them available in London, in Frankfurt, Tokyo, and half a dozen more. All right. Now, when I click Create, the Oracle Cloud will go away. We'll set all this up, and this will take somewhere between 5 and 10 minutes. And at that point, the cluster will be ready for you to log in and use. So you can go from nothing to having a cluster in about 10 minutes.
So back in your molecule analysis days, I guess it would take longer than 10 minutes to set up an HPC cluster at your institution.
Yeah, I mean, well, setting up a new cluster in practice, that takes a year, right? You'd have to go get funding and then do the procurement procedure and whatnot. It might be a little bit faster, perhaps, to apply for an allocation at a national computing center, but even so, you're months and months and months out. So you're quite right. A heck of a lot more than 10 minutes.
So before you keep going, you talked a little bit about storage as you were going through the initial configuration options. When you create, using this tool to create your HPC cluster, what are the typical storage scenarios in terms of working data set? How are people leveraging your cloud for that? Are they using anything local bare metal? What are the common
so that's a good question. So first of all, each of these HPC nodes has about 3 terabytes of local storage that you can use for Scratch or whatnot. So that's in the box. That's
local NVMe, correct?
That's the local NVMe.
Okay.
Then you can attach additional block volumes. That's your network attached storage. And you can share any of this storage out across the cluster over NFS. That's sort of the low-key solution. And in this case, when I'm running just a job on a couple nodes and I know it's not very demanding, that's all I might do because it's super simple. If I have a job that's a little bit more demanding, then I'm going to want a parallel file system, something like Lustre or BGFS or Spectrum Scaler. So, and that can live here in the same private subnet, or it could be in a neighboring private subnet. and that's going to sit on the same low latency network. You're going to have some file servers here running the file system for the HPC cluster. But to date, we don't really need to do that. If you wanted, though, you could set that up in a similar way. So there would be a marketplace solution. It's actually a Terraform stack behind the scenes. And again, you would have a couple parameters to tune, like how much storage you want, obviously, and then you would just click create, and again, you'd go get a cup of coffee, and then when you come back, it would be ready for you.
Okay.
There is also object storage. You see it somewhere off to the side here. It's so that's not a server-based offering, obviously. It doesn't live in a subnet here. But typically, a lot of your objects or your files are going to live in object storage for the long term, because that's very cheap, very durable, very high performing and whatnot. And then for processing, you'll typically stage it into a cluster, either on the local disk, as we discussed, or on the shared file system, or what have you.
Okay.
Does that make sense?
Yeah. Lots of choices, for
yes.
sure.
Too many choices generally is, when you go to the cloud, there are usually a lot of choices, a lot of different ways of doing something. And so it's helpful to have a quick start template like this. So you can just say, all right, give me the vanilla version of a cluster, and I'll log in and I'll customize it a little bit. Now, because what we're doing here is based on Terraform, the additional benefit there is that anybody can take that Terraform template, and you could customize it, and you could customize it to a cluster that looks more tailored to your institution or your enterprise or your team. And then you could use that so that every time you start up that customized cluster, it looks exactly the way that you want it to. Like, it might install a custom image on any of these nodes, or it might stage in files or applications out of object storage, and run a package manager, run some install scripts, or what have you. Right? So that way you have to do the configuration only once, even if you're going to build clusters off of it many times in the future. All right, well, now what I've done is I've set up I actually started a cluster right before we started this call, so that we don't have to wait the 10 minutes for the thing to come up. And 10 minutes isn't very much, but still, we don't have to wait 10 minutes, then that's even better, right?
Yes.
And so I'm, let's see, where am I? Okay. Let me just type this out. So at this point, we can just SSH into the Bastion host. So remember, the Bastion is the one that's sitting in the public subnet, so it's accessible over the internet. And then from there, I can connect to any of the HPC nodes in my cluster. In this case, there's one called Node 20, or whatever name you want to give it. And then that's just a Linux box at this point, so you can install applications. You have administrator access, so you can configure and install it any way that you like. I'm going to go to a directory where I have OpenFOAM computational fluid dynamics model set up, at that point, it's really just like logging into any HPC system. You use your Linux commands, you go around, you launch jobs. This little script here runs computational fluid dynamics simulation just on 72 cores, so just over 2 nodes. So it's a small example, again, so that we don't have to wait long to get any outputs. And then let's see here. I think that worked. What I'm going to do now is I'm going to open a desktop on the Bastion host in my cluster, so that we don't just have to look at this terminal command line, but we can actually see something.
I don't know. Kevin likes to look at command line, but I kind of prefer motorcycles myself.
Yeah, me too. And so this here is the little simulation that we just ran. This was just a very quick simulation of the airflow over a motorbike. So what you're seeing here, let me minimize the browser. This here is actually running on the HPC cluster in the cloud. And the visualization that you see here is basically the airflow over a motorcycle. And if you look at this, so I'm an avid motorcycle rider myself. I just bought a new bike last week that I can't wait to try out. So a couple of things that you see here. You see a lot of pressure here around the wheels. So motorcycles have a lot of turbulence around the wheels. It's one of the reasons that they're actually not nearly as fuel efficient as you might expect compared to a car. You see some happening here in the windshield. That's right and proper, of course. But then you also see quite a lot of pressure here on the motorcyclist's helmet, and then here a little bit in shoulders as well. And so I'm guessing what we're seeing here is that actually this windshield isn't really doing an amazing job because this guy's head is probably sitting in some rather choppy air and might be having a loud and somewhat uncomfortable ride. So you can see how this sort of visualization would be really useful when you're designing vehicles. We do work with automotive customers. For example, Nissan has talked on a few occasions on how they run these kind of simulations on Oracle. Again, you want to simulate the airflow in the case of a motorcycle to make sure the rider is comfortable, but also for fuel efficiency, right? Because air drag is one of the main reasons that your vehicle might not be so fuel efficient. What else do they simulate? Crash tests, right? Doing real physical crash tests is very expensive, so you're going to do lots of simulated ones before your vehicle is ready for an actual physical crash test and before it will be certified as safe enough to go to market.
Well, yeah, I mean, I guess when you can iterate so quickly like this, why not use as much modeling as possible until, in the case of the motorcycle design, until you actually have to go produce the piece. You want to do the work now before you get to the final prototypes or early alpha versions of hardware. You could map out and reduce, I would guess, dozens of iterations, if not more, by using tools like this.
Exactly, yes, exactly. The simulations are relatively cheap. And then because you're in the cloud, you can scale your capacity. You might only be using 1,000 cores of compute today, but then next week you might go to 10,000 cores or 20,000 cores because you're in a major design phase and you need to get through a lot of these simulations as fast as possible. And in manufacturing or in industry, the speed at which you can work through a set of simulations is directly going to translate to time to market, right? If you work in science, then maybe it's time to publication or time to discovery or something like that. But it's often time to market for a lot of our industry customers. And obviously, what we ran here was just a kind of a little demo job, a very coarse, very low resolution. But in real life, you would be using many more cores to do a much more fine-grained, much more accurate simulation. So what that means is that you would be dividing, you would put a spatial mesh basically on this vehicle that you would make much finer, and you would simulate the airflow with much greater detail and accuracy.
And so you might use a smaller version of this sim now when you're early on in design, but as you get more advanced and need more data points, then that's when you might scale up your workload.
Yeah, that's quite possible. There could be all sorts of patterns and rhythms to that. But what we do know is that a lot of our customers will have sort of a fluctuating pattern over time, where the amount of compute they need varies between the baseline and the peak. And again, if you're running all your HPC in-house, then you either have to buy enough computers to handle the peak, which means that those computers are going to sit idle much of the time, or else you sort of try to make a guess and make some compromise and buy an amount of compute that's somewhere in between baseline and peak. But then you have to accept there's going to be times that your engineers are going to be waiting on the results of jobs because they're going to be sitting in a job queue potentially for a long time. So it's nice
Well,
when you don't have to
I
make.
mean, these workloads just lend themselves so well for the cloud because, like you say, the equipment required to do this on-prem takes so much time to budget for and plan for and then requisition time on. I mean, this is just so dead simple to log in, poof, it's there, and off you go.
Well, yeah, it might be a fraction of your overall workload, but that fraction amounts to a massive investment if you had to acquire all those systems.
Yeah, and I think, and Kevin, maybe you've got some thoughts here too. I mean, we're talking about high-end modeling of race cars and motorbikes, which is great. But since the launch of this, and I'm just guessing, but you tell me, have you seen some enterprise adoption for? It just seems like an easy place to go try some of these next gen workloads for orgs that are either dipping or further getting into the pond with these AI ML kind of things. Are you seeing some enterprise adoption and not just traditional HPC?
Yeah, for sure. So we have a bit of both. We have customers that are doing the computational fluid dynamics, the molecular dynamics, and so on, all the traditional, typical HPC workloads. The primary interest that we see from AI and ML consumers is for GPU capacity.
Right.
So they often go through phases where for a few weeks or a few months they need a huge GPU farm basically to train some massive model. And again, it's nice if you can come to the cloud, get those GPUs quickly, and then use them for that duration that you really need them. And so we have A100 Ampere GPUs that are pretty popular for that reason. There's a lot of demand for those for various types of AI/ML, let's say.
Well, it's very cool. I mean, you guys continue to innovate. We didn't talk a lot about networking backbone, but I know that's a big component of why you're able to do this so quickly, to stand these things up. But yeah, really impressive. For people that want to learn more or go try this out, what's the best way to engage or test out the HPC instances in Oracle Cloud?
Yeah, so we have a website. Let me pull it up again. Where did that go? This must be it, right? Oracle.com/cloud/HPC. That's certainly the easiest place to go and read up a little bit on what we offer, get some more details on this low latency network, the bare metal instances, and so on. And then people are, of course, also very welcome to reach out to us. I wonder if we have some kind of contact function on this page. Well, maybe not, but you're very welcome to.
Yeah, there's a little thing down in the bottom right corner, the contact.
Presentation, and oh yeah, there it is. Very happy to let people reach out to the HPC team or myself directly, and talk to them and find out what we can do for them.
Well, that's great. Kevin, thanks for the walkthrough today. Really appreciate it. Good to see these things continue to improve. And for this, Kevin, I don't know if you know it yet, but you've got some work to do on those Ampere instances.
Should be pretty fun.
Yeah, so we'll be back with more Oracle Cloud content very soon. And again, thanks again for participating.
My pleasure. Thanks very much for having me.